Here we are on page 9 of Vector Apps Addendum. These first few plane identification exercises, these you're going to find on the page 8 video. Now we're going to go right to using row operations to solve a 3x3 system. So what does a 3x3 system look like? Well, the reason why they call it 3x3 is because it has 3 variables, which are x, y, z. And it's got 3 equations, as you can see here. 1, 2, 3 equations. Okay, when you take these 3 equations and you solve them as matrices, what you do is you take the coefficients a1, a2, a3, b1, b2, b3, c1, c2, 3c, and the right-hand side d1, d2, d3, and we put them in what we call an augmented matrix. The augmented matrix has an extra column on the right side with a vertical line here. The vertical line is to represent the equal signs here. We do row operations on augmented matrix form to achieve echelon form. What is echelon form? Echelon form looks like this, where the lower left part of the matrix is all zeros, and the upper right part of the matrix, starting from the diagonal to the upper right, is not zero. And then, of course, the numbers on the right are either 0 or not 0, depending on what is left over after you do a bunch of row operations. So we change augmented matrix form, which is that, to echelon form, which is that. And the reason why we're doing that is because we're reducing, especially the last row, to a very special format, which is equal to h on the left and I on the right. Remember that the h on the left is a coefficient, and it's a coefficient being multiplied times the variable z. So when you have h and I left over, what you're left with is hz on the left and I on the right. Once we have hz equals I, remember that h and I are actually numbers. So you can solve for z by dividing I by h. After you find a number, a numerical identity of z, you can take the z value and then plug them back into the other equations, which can be found here and here. Like, for example, EFG actually means EY plus FZ equals G. And this is a pretty good way to find the value of y if you already know the value of z. If you know the value of z, you plug it in there, and then you can easily find out the value of y. We'll do some examples like this in this page. Okay, so if h is not equal to 0, we identify a unique solution. The unique solution means we're going to get a solution, a normal, like a solution we normally expect to get, which would be h equals a certain number, y equals a certain number, and z equals a certain number. And they're all specific numbers. If h equals 0 and I is not equal to 0, that means that at the very end we're going to have something like 0, z equals like some number that's not I, like 7. Now, 0 times z is 0, right? 0 equals 7 makes no sense. So, basically, that would yield no solution, and it would be an inconsistent system. If h equals 0 and I is equal to 0, then you would end up in the last row with 0 equals 0, which is always true no matter what the value of z is, right? So that would mean there would be infinite solutions, okay? All right, let's move on to a real problem here. We're going to solve the following system using row reduction, which is, we are going to start with augmented matrix form, which I'm going to write here. The way I make augmented matrix form is I use 1, 2, negative 3 for the first column. I use negative 2, negative 4, 6 for the second column, and I use 5, 8, 7 for the third column. And the fourth column, the augmented column, is 1, 2, negative 3. So here I'm going to write out all the numbers. Positive 6, and 5, 8, 7. And the last column is going to be 1, 2, negative 3. Okay, and now I'm going to reduce these columns by row reduction. Remember that to do row reduction, I can do I can scale a row by a factor, with multiplication. I can add one row to another, or I could invert two rows. Okay? So the first thing I'm going to do is I'm going to use the first row to try to reduce the second row's first element. Remember how some of these elements should be changed to 0 by row reduction, and it happens to be these three elements. I can see how I can eliminate the 2. I could multiply the first row by -2, and then I can add it to the second row. So why don't I do that? So if I multiply the first row by -2, I would have -2, 4, and -10, and -2. So I'm just going to put those in parentheses now so I could remember them. And I'm not actually going to change the second row. I'm just going to leave the second row as is. But I am going to take these values here, which are the first row multiplied times -2, and I'm going to now add them to the second row. So when I do that, 2 plus -2 is 0. Now I'm going to take 4 plus -4, and that also makes it 0. We didn't really mean to do that, but okay. And then we take the final one, -10 plus 8, and we get -2. And then we take our -2 value and add to 2, and we also happen to get 0 for that. Okay. And then for the last row, let's see, we have -3, 6, 7. We want to get rid of at least the -3 and the 2. What if we took the first row and we multiply it times 3, and then I already wrote minus times 3 here. So we're going to take the first row, we're going to multiply it times 3, and then we're going to add it to the third row. Okay? So 3 times 1 is 3. Add it to -3, and this becomes 0. We take the -2 and multiply that times 3, -6, and we add it to 6, and we get 0 here too. And then finally, I'm going to take the the 5, multiply times 3, we get 15, and then I add it to the 7, and we get 22. And then I take the 3, and I multiply times 1, I get 3, and then I add it to -3, and I get 0. So now we can see that from the last two columns, we are going to have the following equations. -2 times z equals 0. And 22z also equals 0. Actually, the only thing that we're going to get from these two equations is the fact that z equals 0, right? Because -2 times z is equal to 0. And if 22 z equals 0, then that means z is equal to 0 divided by 22 also. Actually, z is equal to 0, right? So now we know that z is equal to 0, and the second row told us that, and the third row also told us that. Okay, now we're going to take the first row and we're going to rewrite it as an algebraic equation. Do you see how I took the coefficients 1, -2, 5, and I wrote them here? Okay, and then the 1 on the right-hand side became the 1 here. Now I am going to take my z, which we know is always 0, and I'm going to substitute it in here. That eliminates the last variable. And now we have 1x minus 2y equals 1. Okay. Then we have x minus 2y equals 1. Okay. And then we are going to see that x and y's values are not fixed. Okay. This is not going to be a unique solution. So we know that z is always equal to 0, but x and y's values are kind of related. So let's rearrange this here. We're going to write x equals 1 plus 2y. So if we know that the y value is a certain value, then we know that the x value is going to be 1 plus 2 times the y value. Okay? So let's fix the y value as related to the parameter t. And then we can say that the x value is equal to 1 plus 2 times t. Okay? So now we have first a fixed value for z. And then for x and y, we can use the t parameter to create all the related values of x and y. Okay? So that is the solution for 1. There's an infinite number of solutions. Z is always 0, but x and y can have variable results, and they depend on each other. Let's do 3a. Discuss the possible solutions of the following systems where k is a real number, and interpret the solutions geometrically. I want to go back and show you the different orientations that two planes can have in space. Let's pay particular attention to these first two, okay? So you could have planes that are parallel, that never touch, but are different planes. Then you could have planes that intersect each other. And when planes intersect each other, they're going to invariably look like this. You can like turn them in a certain way so that they'll always look like this. And the intersection of two planes is going to be an intersection in a line, right? This is an uninteresting solution, which is that the two planes are the same plane. Okay, so there's intersecting and parallel. Let's go back to the problem. How do we know whether planes are parallel or intersecting? Well, remember that the equation of the plane tells us the orientation of the plane. And where do we see it? We see it by the coefficients of x, y, and z. By the coefficients of x, y, and z, we can determine what the normal vector is. And if the coefficients of x, y, and z are the same or similar or proportional in one plane equation relative to the other, we know that those planes are parallel. Now, in this case, depending on the value of k, the values of the coefficients of x, y, and z might be proportional, right? So in the first one, I have 1, 2, negative 1, right? In the second one, I have 2, 4, and k. Do you see how these kind of maintain a proportionality? So, what would k be to make the second set of normal vector numbers? How would we make it proportional to the first set, 1, 2, negative 1? Well, you can get 2 and 4 by multiplying 1 and 2 by 2. So if we take the third number, negative 1, and we multiply by 2, then k becomes negative 2, right? So k is negative 2. If k is negative 2, then the first set of coefficients is proportional to the second coefficients, which means the first plane is parallel to the second plane. So if k is equal to negative 2, we know that the two planes are parallel. Now, we see if not only are they parallel, but maybe coincident too. Well, let's do the following. We'll take k equals negative 2, and we'll plug it in for the k value and see what happens to the equation. So the first equation is 1x plus 2y minus z equals 6. We're going to put k equals negative 2 in there, and we're going to get 2x plus 4y minus 2z equals 12. Now, if you look carefully, you can see that not only are the coefficients 1, 2, negative 1 and 2, 4, negative 2 proportional to each other by a factor of 2, what happens if you multiply the 6 on the right-hand side by 2? You get 12, right? Wow, so actually the first equation and the second equation are actually the exact same equations. They're only different by a factor of 2 on the left-hand side and on the right-hand side. If they were the same on the left-hand side but not on the right-hand side, then you would say that the planes were parallel because they share the same normal vector. Then you would expect the right-hand side to be different. Okay, they would be parallel but not coincident, not the same plane. But if the right sides are also the same or proportional, that means that actually it is the exact same plane. So not only are these parallel, but they're also coincident. Okay? Coincident. Okay. Let's look at the second system. In the second system, we can vary the k value here. Now, is the left side proportional? Oh, one more thing. Let's go back to A again. One more thing. What if k is not equal to negative 2? If k is not equal to negative 2 for part A, we would end up with two planes that are not parallel, because if k was not negative 2, then the coefficients 1, 2, negative 1 would not be proportional to 2, 4, k, or, k would not be negative 2 in this case. So that means if k is not negative 2, that means that the two planes are intersecting, right? Because if they're not parallel, they must be intersecting. Okay. Let's go back to B again. What about B? We have these set of coefficients. We have 1, negative 1, 3, And we have 2, negative 2, 6. Ooh, these are also proportional, right? So if the left side is proportional, 1, negative 1, 3 is you could multiply each one of these elements by 2, and then you could get the second set of coefficients, 2, negative 2, 6, right? So, yes, they're parallel then, because they share the same normal vector or the same coefficients. So we do know that these two planes are parallel. Now, are they coincident? Well, to be coincident, the right-hand side would also have to be proportional. So we can get the second set of elements by multiplying by 2. So if k is different by the top number 8 by a factor of 2, if it was 16, for example, then we would say that they were not only are they parallel planes, but they're the exact same plane. Okay, so if the top was 8 and the bottom was 16, they're off by a factor of 2. Every single element of B, including the coefficients, including the right-hand side number, are different by a factor of 2. That means that it's the exact same plane, because all I need to do to change the first equation to the second equation is to multiply the first equation by 2. All right, so that means that if k equals 16, that means they are the same plane, so we would say it's coincident. Okay? Now, what if k was not 16? If k was not 16, they are parallel, but they're no longer the same plane. They're just parallel planes. So then, if k is not equal to 16, we would say that they are parallel planes. Okay? And that is it for page 9.